I'm Anton Bilbano.
And I'm Jason Mulesy, and we're Group 2, the wireless hand sensor.
The design process is very important. First, you should always breadboard. Test every single customer requirement and engineering requirement, making sure that the breadboard works. Then you can move on to the PCB and finalize your design.
One thing I would recommend to seniors next year would be to start early and to plan a lot up front. What we did was we planned our block diagram very carefully and painstakingly to make sure all the connections would work correctly and that all the interfaces were properly defined. Setting that up right from the beginning made it very clear what we needed to get done, and we didn't have to change a lot of things throughout the process.
Communication is very important.
It's so ironic. The purpose of this project is to allow a user to wirelessly control the computer via a glove on their hand. Douglas Engelbart at Oregon State College developed the first computer mouse. The usefulness of the mouse has not diminished since it was invented. Alternate forms of the mouse have been created in the past, with the addition of extra buttons and scroll wheels. This project attempts to further alter the concept of a mouse into another form, including various shortcuts to give further control over the computer.
This project involves a glove fitted with various touch sensors and an inertial measurement unit. The touch sensors allow the user to perform various actions, such as left click, right click, and other shortcuts. The inertial measurement unit allows us to monitor the rotation of the hand while ultimately control the mouse pointer. When we refer to touch sensors, what we are really referring to is these sewn-on conductive fabric pads. The conductive fabric has some resistance, but it's negligible. The thumb is pulled to a high level voltage, and when you touch it to any pad, we are able to detect changes in this voltage using the analog to digital converters in our microcontroller. What you are currently looking at is our first design. You can see wires going off in various directions, and you can also see the Bluetooth module to the left of the bigger PCB. Now, here's our second version. The RN42 Bluetooth module has 4 pins that insert into the RX, TX, 3.3 volt, and ground pins. Supported by the 4 pins, the Bluetooth board also rests nicely against the battery connector. Although this is not necessarily a unique design aspect, Bluetooth was a great choice for the product because it does not require an additional receiver that must be carried around with the glove. Once you turn on the glove, if you have a Bluetooth-enabled computer, it will automatically find the device. Controlling the wireless hand sensor is fairly simple. The mouse is controlled by moving the hand at the wrist. Left, right, up, down, move exactly as you think it would. To execute an action with the conductive pads, simply press your thumb to the pad. By default, the tip of your pointer finger is left click and the tip of your middle finger is right click, just as you would expect with a regular mouse.
Takes 5 seconds, so the user has enough time to keep the hand still. And to reset, the values go back to 0 and the user is ready to go again. Press a few buttons. And when you press a button, zeros turn to ones. We can do some clicks, X out of Windows, go to text, so we can select text, we can do a copy, various different things such as minimize.
Here we have Mushfiq standing at the door with the glove on, and we have our computer over there. So now I'm going to walk over. Run the script. Now he's going to calibrate the glove. And now the mouse is moving again. And he's still over there.
Here you can see Mushfiq demonstrating the glove on Google Earth. Watch as he holds down on a finger and points up and down to zoom in and out, or makes a flicking motion to make the Earth spin.
Our first block is a voltage level converter, which is using a TPS 77633 from Texas Instruments. It takes an input of 3.7 volts from our lithium-ion battery and bucks it down to 3.3 volts, which all are components such as the IMU and the microcontroller use.
The touch sensing block incorporates touch sensors and a multiplexer. Due to the limited number of pins on our microcontroller, we use a multiplexer in order to check the status of each conductive pad. Each pad is hooked up to a pin on the multiplexer, while the microcontroller cycles through which pin it wants to read. In order to cycle through all 8 of our pads, the microcontroller needs 3 output signals. This is because you need 3 ones or zeros to count to 8 in binary. A 4th signal comes back from the multiplexer, which is the status of the pad you want to reach.
The IMU block features a MPU 6050, which is an integrated gyroscope and accelerometer. It is run via I2C from our microcontroller. The raw values from the gyroscope and accelerometer are used to calculate the angles of rotation using our filter algorithms.
Next block is the LED feedback block. This block was implemented because we wanted users to know every time a button was pressed. The basic structure of the block is it uses a shift register to extend the output of our microcontroller from a few outputs to as many as we'd like, but we used less than 8. Basically it has a few control signals sent to it that enable the shift register to latch data out, and it uses a power and ground connections to power the LEDs and the shift register. Another block we have is the computer block. This block is comprised of the physical connections to the computer and the Python computer code that goes into it. The Python script is actually a driver and a graphical user interface application that read the information sent by the microcontroller and convert it to mouse movement and button clicks on the screen. The graphical user interface can be used to customize the macros so that each specific touchpad on the fingers can correspond to a different action, so users can set up exactly how they would like the device to perform.
The transmitter block is comprised of the RN42 Bluetooth module made by Roving Networks. It is powered off the 3.3 volt output of the voltage regulator. It is connected to the microcontroller using the RX and TX pins, as you see here, over UART. The microcontroller we use is an ATmega 328. It operates on 3.3 volts at 8 MHz. The microcontroller is responsible for checking for touches on the conductive pads, updating the status of the feedback LEDs, receiving the raw data from the IMU over I2C, applying the filter algorithms to this data, and then sending out the calculated angles and button statuses over UART.